Just to remind you, the last slide that I showed, just mentioning this kind of stability, this new kind of stability, dynamic kinetic stability that could help explain the transition from some simple replicating entity to complex life, and this concept of dynamic kinetic stability. But one has to stop for a moment and say, why two stability kinds? It sounds a little bit ad hoc, you know. You make a new stability because it suits you, because it explains things. Stability has this, you know, one sense aspect to it, and I now want to try and show you how the different stabilities can come together as one. Recently, some years ago, together with a wonderful collaborator in France, Robert Pascal, we proposed a principle, the persistence principle, as a general rule governing change in the world, a general rule. And the rule can be expressed this way: things tend from less stable persistent to more stable persistent, or to put it in more simpler terms, nature drives towards persistent forms. Now, this is not an empirical rule in our view. It's axiomatic, it's logical. And why do I say that it's a logical rule? I think everyone in this room will agree with the following statement: unchanging things don't change, and changing things do change until they change into things that don't. So things will tend to change from less persistent to more persistent logically. And the other thing to notice about this persistent principle, it's about time and not energy. Often when we talk about stability, because of thermodynamic stability, we're talking about energy, entropy, Boltzmann. But there's another kind of stability which is about persistence. If you say a couple have been married for 50 years, they have a stable relationship. Nothing about energy there. It's persistent, it's stable in time terms, not in energy terms. What's the connection, the relationship between time and energy in terms of this stability concept? I think it can be shown with this Venn diagram, which shows that the general class of persistent systems, thermodynamically stable systems, are a small group, a subgroup within that general class. Thermodynamically stable systems are persistent because when a system has reached thermodynamic stability equilibrium, it persists. It's got nowhere to go. So it becomes persistent. So thermodynamically stable systems for energy reasons are persistent for time reasons, because that's it. They don't do anything anymore. However, persistent systems don't have to be thermodynamically stable. And that's something that I just showed. And specifically, kinetically stable systems sit in this blue area of being persistent without being thermodynamically stable. So the bottom line here is that stability based on time, persistence, is more general than stability based on energy, which is Boltzmann's thermodynamic stability. But what this means is we seem to have identified two evolutionary paths towards persistent systems. You can get persistent forms. You can get to persistent forms either in the regular world along Boltzmann's probability path towards thermodynamic stability based on Boltzmann's entropy equation. But there's another pathway to persistence, which is through, let's call it Malthus's exponential growth with that exponential differential equation, which leads to a different kind of stability, this dynamic kinetic stability. The point is that both processes, both pathways are underpinned by mathematics. In other words, it's not just conjectural, it's not empirical, it's logical. Boltzmann's thermodynamic stability is logically based. It's based on probability theory, and dynamic kinetic stability also has this mathematical base. But because there are two maths, different maths that describe persistence, we have two material forms, each expressing the underlying mathematics in different ways. So just to clarify that, why the fact that there are two maths, we have two worlds. There's the regular world that we're all familiar with. Things are stable, persistent because they do not react, and that's thermodynamic stability. And in the replicative world, things are stable, persistent because they do react to make more of themselves. And that's the dynamic kinetic stability. And remember those, well, I'll show it in a moment, but I'll mention it now anyway. Remember those cyanobacteria. They're very persistent, billions of years. So, you know, you can't argue with that. They're just there because they're good at making more of themselves, and they continue to do it. Oh, here's the, okay, I should have left that out, but here is the pictorial example of what I'm saying. In the regular world, you see here the chalk cliffs off the English coast. They've been around for 60 to 100 million years, reflecting thermodynamic stability. That's quite a long time. That's very stable, 60, 100 million years. And why are they stable? Because they don't react. So they're there. They continue to be there. But here on the right-hand side, we see two examples of stability in the replicative world. Ants, I'm told by biologists, have been around in one form or other for 140 to 160 million years, longer than the cliff, the chalk cliffs. And the cyanobacteria that I just mentioned, 2 to 3 billion years. And this stability is dynamic kinetic stability, stability, persistence through self-replication, things that are good at making more of themselves. And now an interesting question is, how do you measure progress on this path towards persistence? Well, in the regular world, the answer is increasing entropy. That's Boltzmann's big contribution. What happens? What's the measure of progress in the replicative world? And the answer I propose is increasing complexity. And that increasing complexity, one can think of it as a second law analog. The only problem with this idea of increasing complexity is we don't know how to define complexity. We certainly don't know how to quantify it. Entropy, of course, is quantifiable. So here we have a problem or a challenge that we're talking about something that is hard to nail down in a very precise way. But first of all, let me justify what I've just said. What happened over evolution in the biological, in the replicative world? We went from a simple replicating system to simple life, and then to complex life, and it's been increasing complexity all the way. Let's just look at that in detail. The chemical phase, the first phase, clearly that has been one of increasing complexity because a simple replicator became simple life, and simple life is very complex. We already know that. A bacterium is unbelievably complex. But once we go to the biological phase, we still seem to have this process of complexification. We started off with prokaryotes, which then evolved to eukaryotes, then multicell organisms, and then ecological networks. The system seems to continually complexify. There's an issue here that biologists can raise questions about, and I don't want to get into it now, but part of what I've said now is debatable, but to go into that in detail would take too much time, so I don't want to do it now. But I think broadly speaking, this is correct. The biological phase also is about complexification. If you want any just more evidence for life's complexity, here is a map of metabolic pathways. and you'll be relieved to hear that I'm not going to say anything more about that. But you can see it's very complex. And here is the ribosome, that remarkable machine of molecular weight, 2.5 million Daltons, that makes proteins as a result of the messenger RNA coming in with the sequence, the required sequence. So there's no question that life is complex. And then we have to ask, why complexity? Why is life complex? A wonderful experiment conducted by Jerry Joyce, published in Science in 2009, I think gives a hint as to the importance of complexity. He created, at least theoretically, a library of 10 to the 14th RNA molecules, a big library of RNA molecules, and he wanted to pick out the best replicator. We've said RNA can self-replicate, the best replicator from that library, and he found it. Let's call it T, and it wasn't a replicator that could bring in lots of building blocks to make a copy of itself, but just 2 building blocks. T is simply made up of an A and a B. Very simple, 2 building blocks to make a T. And this T was able to link A and B together to make another T. Here's the T, here is the A, here's the B, and it made another T. So that's autocatalysis. But the reaction was slow and limited, showed limited exponential growth. In other words, 1 or 2 cycles of replication and the thing just died, stopped working. But when he fished out of that library of 10 to the 14th RNAs, he found 2 RNAs. He looked for 2 RNAs, neither of which was very good at making copies of itself, but the 2 were special in that one was able to make a copy of the other, and the other able to make a copy of the one. So you created a little network that was autocatalytic, that was self-copying. So it's a little bit complicated to see, but basically E prime makes E through joining A and B, and E makes E prime through joining A prime and B prime. So this little network is self-replicating, and guess what? It was much faster, and the exponential growth was sustained, was self-sustaining, provided that building blocks were provided. So the message here seemed to be that complexification enhances the replicating ability at the molecular level through network formation. So what is the complexification principle? In non-scientific terms, I'll scratch your back if you scratch mine. Here are 2 horses. Horses' legs were evolved for running, not for back scratching. So if horses want to have their back scratched, they have to scratch each other's backs. And this is what these 2 horses are doing, scratching each other's backs. And in the same way as these 2 molecules were helping the other self-replicate. And we can see that the complexification concept in physics, chemistry, seems to now could be translated into cooperation in the biological world. And we see that this complexification cooperation enhances replicating ability, DKS if you like, at both chemical and biological levels. Complexification is an important principle for replicative processes. But we have to go another step. This complexity concept is really a nightmare. Physicists view it differently to biologists, and mathematicians try to quantify the concept. It's a very tricky concept, but I want to, in the context of what we're talking about, I want to talk about different kinds of complexity in terms of function. Here you see a garbage pile, which I call disorganized complexity. It doesn't matter where the junk is, it's the same level of complexity. You can move stuff around. It's still a garbage pile. Nothing's changed. Here you have a car factory, and it is organized in functional complexity. If you move one piece of machinery from one point to another, it stops functioning. It'll only work if everything is in the very place that it has to be. So it's a complexity of a different kind because of this element of function. And when we think about the biological cell is like the car factory. It's highly organized and complex, but the complexity is functional. If all the bits in the cell aren't where they're meant to be, the cell won't do its job. So first of all, to make clear that functional complexity is very different to computational complexity, or the mathematical complexity that physicists tend to talk about. And that leads us to the question of, how did function emerge? Where did function come from? Because in the material world, the physical chemical world, there is no function. Function doesn't exist. Function is something that emerges out of the biological world. So part of the difficulty in understanding the origin of life is, and Jacques Monod, that Nobel Prize winner, the writer of that marvelous book, Chance and Necessity, said the central problem of biology is to explain how did purposeful systems emerge from an objective universe, a universe with no purpose. And yet suddenly you have all of these things, you, me, and everything else, everyone with its agenda and its wanting to do things, you know, from all the way down to the cell, where every component has its function and purpose. Let me just say a little bit more there, though basically I just said a lot of it now. In the regular physical world, no function. Iceberg, sand, rocks, no function, they're just there. That's the material world. The biological world, function is everywhere. The protein with its function of catalyzing a particular reaction. There's the picture of the ribosome. We all know the function of the heart. And I don't have to explain to you what the function of those teeth are. Everything function all through biology. What is the origin? Where did function come from? If you think about it, we've said that in the DKS world, the replicative world, the drive is from DKS less stable to DKS more stable, from poorer replicators to better replicators. So replication has become, through that process, has become a function. The function of replication, and I think replication then can be viewed as the primal function, the first function that emerges from the existence of this other stability kind, the dynamic kinetic stability, DKS. And then any entity that facilitates replication becomes, you think of it as a functional entity, and I've discussed all of those, they're all functional, because they help, they all facilitate the primal function of replication. But of course, non-biological entities can also facilitate replication. Here you see the beaver dam that the beaver builds so that it can make its home in the river. So that has a functional basis, a functional reason. The termite mound, obviously that's not biological either, and it helps the termites replicate, that's their home. I don't know what to say about this. This is the White House. I guess that has a function as well, but let's leave that. That's political. The point is, all function has its roots in biology. That's the key point here. And then one notices that function and complexity are related. There's a relationship that joins the two, and I think this can be seen with this simple illustration. We see here the Wright brothers plane. Very simple, but not very good for flying in. And then 60 years later, you have these 747s, which are a lot better at flying than the the Wright brothers plane, 1903, but it's become much more complex. The complexity has facilitated function. Okay, the complexity has come about to enhance function. Here the function, of course, is the flying function. Less functional, less complex, more functional, more complex. Complexity here simplistically described as the number and diversity of components. I said that's always a problem to define, but that's a simple definition that more or less serves our purpose. And then one can say the moment natural function emerges, natural function, the replicative function, nature begins to act as an engineer, the beginning of complexity. In other words, once nature, excuse me for this kind of language, discovers the importance of complexity in function, it does what an engineer did with the planes. The plane becomes more functional through complexity. Nature discovers the same thing and therefore moves towards greater complexity for greater function, which improves the dynamic kinetic stability. Function, stability, complexity are all go together. So when we say the DKS replicating system driven towards greater DKS, towards complex life, the chemical phase is really just the low complexity regime. The biological phase is the high complexity regime, and the trend in evolution is towards greater functional complexity for greater stability, the reason for the greater complexity. And if you want a vivid example of that, just think of a replicating molecule and a bacterium. If you want a replicating molecule to replicate, you need a lab, students, grants, fancy equipment. And I can tell you, talking to systems chemists, that even with all of that, the replicating molecules can be quite, uncooperative, and sometimes they won't replicate. On the other hand, bacteria out in the backyard, in the soil, doesn't matter, you don't have to worry about students, grants, equipment, happily making copies of themselves continually. Why? How can they do this? Because of their complexity. The complexity has come about in order for that system to deal with all the possible external circumstances that might prevail. So one can say extraordinary function requires extraordinary complexity, and that is like harking back to something that Carl Sagan once said, extraordinary claims require extraordinary evidence. You familiar with that expression? It's a very good one. Living things, the bacterial cell, extraordinary function. I mean, what it can do is just unbelievable when you think about it. And it has only been able to come about through extraordinary complexity. A question that Erwin Schrödinger, that great physicist, asked, now why are atoms so small? Tell me, can anyone but a physicist ask a question like that? Why are atoms small? But then he went on and said something interesting. Clearly the question is an evasion, for it is not really aimed at the size of the atoms. It is concerned with the size of organisms, more particularly with the size of our own corporeal selves. So it's not that atoms are small, the issue is that we are big. And then the question is, why are we big? And why are living things so big? And here's the answer, because extraordinary complexity, I just told you, is essential for extraordinary stability. For us to be stable in the replicative sense, we have to be complex, and that's why we are big and atoms are small. A few words about the RNA world, because it also fits in with this general idea of complexity. Life, as we now know it, of course, involves the dual world of nucleic acid and proteins, the nucleic acids with their emphasis on, let's say, replication, heritable replication, information, and the proteins with catalytic function. But some years ago, Czech and Altman discovered that RNA can act as a catalyst. You can have catalytic RNA, and the term ribosome. A catalytic RNA came into being, and that RNA is not just good for replication, but it also can catalyze, and they got the Nobel Prize for that discovery. But the implication then from that was that a simpler RNA world preceded the more complex dual world of nucleic acid and proteins. And in fact, there is evidence, a nice piece of evidence that supports this idea. We've already said the ribosome is the machine that generates proteins. But when one looks carefully at the structure of the ribosome is made up of RNAs and protein molecules together. But when one looks at the ribosome carefully and we color the RNA segments silver and the protein segments in gold, we notice something interesting. The place where the protein or the amino acid chain is generated is shown here by that dot. That's the heart of the ribosome. All of the area around that, the central part of the machine, is silver, RNA. Protein is only in the periphery. So there is a strong view that the early life forms, the early RNA would have been, the early ribosome would have been just RNA, because that's what was there. And with evolution, protein became incorporated into the ribosome, but this was already fine-tuning to get it just right, to get it to improve it. But the ribosome is fundamentally an RNA machine, if you like, a ribozyme. So here it is. The structure of the modern ribosome suggests that the primal ribosome was built up from RNAs only. Proteins are only found on the periphery. And then this business of 2 versus 1, again, this is a logical idea. Division of labor, it's well known in economics. 2 is better than 1. A dual nucleic acid protein world would have been more functional. It's more complex, but it's more functional than the simpler nucleic acid world alone. Remember, the 2 replicating molecules doing a better job than the single replicating molecule. And here I have another visual description of this. This is my daughter trying to eat Chinese food on the left with 1 chopstick and not making much progress. And on the right-hand side, doing a lot better with 2 chopsticks. So it's easier to eat Chinese food with 2 chopsticks than with 1. The division of labor, 2 is better than 1. So here, just the basic idea, improved function almost invariably requires increased complexity, a general principle, an engineering principle, one might call it. And that all leads to what one might call a physical theory of evolution, not a biological theory, a theory with its roots just in physics, all stable, physics, chemistry, all stable, persistent, replicating systems will tend to evolve primarily by complexification towards systems of greater dynamic kinetic stability. And you'll see there's no biological terms there, so that principle would apply for both biological and chemical systems. And then we can see in a similar way that the many Darwinian concepts that we're familiar with are really applications, particular applications of broader physical and chemical concepts. We're familiar with natural selection, fitness, survival of the fittest, cooperation. These are just the biological jargon for more basic ideas: kinetic selection, dynamic kinetic stability, survival of the fittest, the drive towards greater stability, dynamic kinetic stability, cooperation, complexification. Biological concepts firmly rooted in physics and chemistry. Biology is ultimately a complex manifestation of replicative chemistry. I want to say something now about design, because we often talk about, in the biological context, design. Richard Dawkins has been arguing that natural selection can produce an uncanny illusion of design. So we all agree that this submarine was designed, and the similarity between the shark and the submarine is extraordinary. So is this design or illusion of design? Part of the question is, how do you want to define design? But if you define design in the following way, which I would, design the process directed towards a required outcome, then I'd say nature designs because it has an outcome in mind. I explained the outcome earlier. Persistence. Nature drives towards increasing persistent forms. So if that's the case, rather than calling this the illusion of design, I would say this is just natural design. So this, on the left, we have human design, and this is natural design. Nature designs for persistence. And here's another example of that. Here's the temple at Angkor Wat, designed, obviously. Humans built that. And here's the cathedral in Barcelona, designed by humans. What do you say about that? That's a termite mound, a termite home. If you think that wasn't designed, boy, you know, it doesn't. There we have an example of natural design. That's what I would call it. So I don't know that the term illusion of design is a good term. You know, in English we have the expression, let's call a spade a spade. It looks designed, so it was designed. But of course it wasn't designed. Now we're getting into dangerous territory. I'm not saying a deity designed it, or the design is natural design because of because nature's driving forces, the driving force towards persistence. We have all of these characteristics of living systems that have been troublesome to explain in terms of physics and chemistry, but I think can be understood through the DKS concept. Some of them I've already discussed. For example, functional complexity I've described. I want to say something about this in a minute. Homeostasis, teleonomy, how living things can be purposeful, life's homochiral character, life's extraordinary diversity, and this one, which is, I mean, nothing less than remarkable, cognition. How did inanimate stuff become self-aware and start to act in response to the environment? I won't talk about that one now because we're writing this up and it hasn't been published, but I think within the DKS concept one can find an explanation for that. What I want to now do is just show you a couple of these in the time that we have. So the dynamic character first. Here is a picture of, everyone here is too young to remember these old pictures of Humphrey Bogart and Ingrid Bergman, thank you. In that classic movie, Casablanca. That is definitely Ingrid Bergman, no question. But I have a problem. Here's a picture taken in 1945. It looks like Ingrid Bergman, but I'm just wondering, is it really Ingrid Bergman? Now, why do I say that? This is Ingrid Bergman because the stuff that makes that person Ingrid Bergman is a certain stuff, you know, molecules and all the rest of it. That arrangement of stuff is called Ingrid Bergman. I can tell you categorically that that woman here, the stuff is totally different stuff. It's not, it's different to the stuff that makes this real Ingrid Bergman. So my question is this really Ingrid Bergman or is it a look-alike? So I'm just sort of playing here a little bit, but the point is clear there's something very strange about biology in that biological systems are constantly turning over. You meet someone you haven't seen in a while, it's still that person, but it's all different stuff that's making up that person over a particular period of time. Well, the explanation for that, it's very simple. It's this, the nature of dynamic kinetic stability. It's stability, persistence through change. Just like this is the same fountain in Geneva, the water is continually turning over. And we can actually see these steady states at different levels of complexity. So if you have a molecular persistent system, a molecular replicator, then there's just one level of turnover, and it's just this fountain picture. But at the cell level, we already have two levels of turnover, in the sense that the molecules in the cell are continually turning over, and the cells are continually turning over. For example, proteins in the cell are being degraded and resynthesized in a very regulated fashion, because the structure of the protein has to be exactly right or it won't function. So the proteins in the cell are continually degraded and resynthesized, and intracellular protein has a half-life of between 11 minutes and 48 hours. This is the ubiquitin mechanism for protein degradation. Nobel Prize to Hershko, Chekhanova and Rose, 2004. And basically what we're seeing here is a double fountain, a fountain within a fountain. So cells are turning, the molecules in the cell are continually turning over, like the proteins, and the cells, eventually they're turning over all the time, like the cyanobacteria or the cells in our body. But at the organismic level, we have three levels of turnover. Molecules in the cell are turning over continually. The cells are turning over, like in us, skin cells, blood cells, continually turning over. And here is, I'm afraid to say, some bad news. We're all turning over as well, but happily we're around for a while before the turnover actually takes place. So, and I don't know how to put a fountain in the fountain, so I'm showing pictures with fountains next to fountains, but it's really a fountain within a fountain, different hierarchical levels of turnover, the different complexity. And the last thing I want to discuss is diversity. Life is extraordinarily diverse. I mean, we're all aware of that. And how can, well, here is just the, the phylogenetic tree, just showing how there's this branching out that leads to more and more expressions, biological expression. And the longer we go, we find new species. I mean, this is, the diversity in nature is, in biology is simply astounding. How can we explain the enormous diversity that we have in the biological world as compared to, we don't have that kind of diversity in the regular physical chemical world? Well, I think if we look at it, thermodynamic and dynamic kinetic worlds have different topologies. Let me explain what I mean by that. In the regular world, the thermodynamic world, there is what we call a thermodynamic sink, that all systems that have the same formula or the same material basis are headed towards their thermodynamic sink. If you have a number of isomers of a particular hydrocarbon, they're all headed towards, and oxygen, let's say, then they're all headed towards that one sink, carbon dioxide and water. So thermodynamic space in that sense is convergent. Everything is headed towards its thermodynamic sink. But in the biological world, in the replicator world, this space is divergent. And the reason is because there is no explicit direction that one can increase the dynamic kinetic stability. Depending on the external circumstance, it can be along this path or that path or that path. It depends on what's out there, because the DKS system, the stability of a DKS system depends not just on the system, but on its environment. Bacteria in water can be stable, but if you put disinfectant into the water, the bacteria now are unstable. So the external environment impacts on the stability of living systems, and in that sense the DKS topology is a divergent one. But that explains different facets of the life phenomenon, in particular the extraordinary diversity, because you're going off in all different directions. But it does something else as well. It explains why in the regular world you can't look at a system and learn about its history. The history is inaccessible, because if you go back in time, it's divergent. If you go forward, it's convergent, and that's why if you go into the lab and ask a chemist what will happen if I mix this with that, he can make a prediction because things are headed towards their thermodynamic sink. But in the replicator world, where everything is reversed, it's the history now that becomes accessible, because going back now, the world becomes convergent, and that's why we can trace back our phylogenetic tree, family history, and so on. It's the future that, of course, becomes unpredictable, because once you're sitting at this point here, we don't know if tomorrow we're going to be here or here or here. There's uncertainty regarding the future in the replicator world. So let me then conclude now by some conclusions. That's a good way to conclude the things that I've been trying to say. Origin of life, back to the central question, how and where. These are historic questions, and there is no clear historic record, and it may well be that we won't ever know much more than we know now, because of these historic questions, and the historic record is largely, if not totally, eliminated. Why is the ahistoric question? I think here we've made progress. The ahistoric question, why would inanimate matter be driven towards life? And the answer that I would suggest is because nature's drive is towards stability, persistence, and in the living world, in the replicative world, of course, it's towards persistence of the replicative kind, this DKS. Replicative persistence is derived from, and the motor for this process is derived from the kinetic power of exponential growth. The origin of life, one can think of as the emergence of a chemical DKS system able to complexify towards life. And finally, what is life? One can give it a physical chemical description, definition, a dynamic, energy-fueled, replicative network in the DKS state. The big challenge in origin of life research, in my mind now, in the field, is to create in the lab a dynamic, energy-fueled replicative system, shown like this, vaguely, which would then be able to complexify in that biological direction. As we speak, there are labs around the world that are working on this problem. It hasn't been achieved yet. Once that is achieved, then in some sense, I believe, the essence of the life problem, what is life, will have made a big step in that pursuit, and may start to give us indications of other kinds of life that might be possible by playing around with different chemical systems that can induce this same DKS state. But that's, as they say, for the future. The last slide, just to, first of all, I mean, have to take advantage of the opportunity to plug my recent book, What is Life? How Chemistry Becomes Biology. Second edition appeared a couple of years ago. My collaborator that I already mentioned, wonderful collaborator in a lot of this work in recent years, Robert Pascal from the University of Montpellier. Other people that I've collaborated with over the years. And of course, cost actions, 1304, 1308. The cost action that Muriel, I don't know if she's here, organizes a wonderful one for the interaction one needs with scientists. I kept talking about network formation and complexity. How does science move forward? Through network formation and complexity. We talk to one another. Without that, it's hard to make progress in the scientific field. So I thank them and the places where most of this work was done. Thank you.